Hello students, myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering in ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, I am going to start my lecture second, which topic is transmission line, and the subtopic which I am going to cover in this particular lecture is the transmission line equation. So, basically there are various type of transmission line. So, first one is the two parallel wires, cable, coaxial cable, microstrip line, optical fiber, waveguide and etc. So, in this particular sub lecture, I am going to have the basic description of the two parallel wires transmission line equations. The conventional two conductor transmission lines are commonly used for the transmitting microwave signals. So, if the line is properly matched to its characteristic impedance at each terminal, its efficiency can reach maximum. So, before going through in detail about the transmission line equations, first of all the general features which should be applied in the transmission line. So, first one is the if the matching is proper of each terminal, that means we are talking about the transmission section terminal and the receiving section terminal, and if the characteristic impedance which is generally represented by Z0, if this impedance is matched to the transmission section, that is one to first terminal, and to the receiver section which is our second terminal. So, in that case if the match, that is impedance should be near about equal or equal. So, in that case the efficiency will be maximum, because what is the reason that the efficiency will be maximum? Because if the matching is proper, that means there should be minimum reflection or no reflection. Frequency operation are so high that the inductance of short length of the conductor and capacitance between short conductors and their surrounding can be neglected. So, if in this particular section if the frequencies are very high in the microwave, so inductance of the short length of the conductors and the capacitance between the short conductors and the surrounding can be neglected, because we know that inductance and the capacitance are related to the frequencies. Since the wavelength is short in comparison to the physical length of the line, because we already know that this wavelength is very low in the case of microwave signal, because the frequency is high and the wavelength is inversely related to the frequency. So, the wavelength length is always less as compared to the physical length of the transmission line. Distributed component cannot be represented accurately by the means of lumped parameter. So, distributed component can't be represented accurately by the lumped parameter. Equivalent circuit, thus microwave transmission line can be analyzed in the terms of voltage, current and impedance in the distributed circuit theory. So, one question, that why the distributed circuit theory is used, not the lumped, because the wavelength is short in comparison to the physical length of the transmission line. And if the spacing between the lines is small, so normally we use the transmission line, but what will be the case when we are going to move towards the waveguide? So, if the spacing between the lines is smaller than the wavelength of the transmitted signal, if the spacing between the line, that is first line and the second line, if this spacing between the two lines is smaller than the wavelength of the transmitted signal, this is the transmitted signal, if this spacing is smaller than the wavelength of the transmitted signal, in that case transmission line must be analyzed as waveguide. So, if the questions come, when should the waveguide can be used? In that case you should answer, if the spacing between the lines, two lines of the transmission line is smaller as compared with the wavelength of the transmitted signal, in that case transmission lines should be analyzed with the waveguide. So, in this particular slide you have got the two question, why the distributed circuit theory is used in the analysis in the microwave engineering, not the lumped parameters are, and the second when the waveguide should be used. Now, now we are moving towards the transmission line equation. So, transmission line equation can be analyzed by the two methods. First one is the Maxwell equation and the second one is the distributed circuit method. So, why we are not using the Maxwell equation? Because the solution of Maxwell equation involves three space variable in addition to the time variable. Space variable, I think you are aware, space variable x, y, z are basically our space variables. So, when we analyze the transmission line equation with the help of Maxwell equation, in that case we have to analyze the equation with the three space variable and one time variable. But when the distributed circuit method comes into existence, only one space variable z and one time variable. So, of course, we can say that the analysis will be easier in the case of the distributed circuit method as compared to the Maxwell equation method. So, in this particular analysis of the transmission line equation, I am going to use the distributed circuit method. Now, here I have taken a small section of the transmission line whose length is the, of course, very minimum del z, and the analysis is done on that. Consider uniformly distributed. So, what we have considered before doing anything, we have to assume something. So, here we have assumed that all the distributed circuit are uniformly distributed over the complete length. So, that is why we are able to take a small part of that. If it is not uniformly distributed, it is very difficult for anyone to analyze the circuit or anything transmission line by taking a small part of that. So, I am able to take a small part of that by assuming that uniform distributed circuit theory, that is everything is distributed throughout the length of the transmission line uniformly, and assuming wave propagation in the positive z direction. We have to take only one space variable and that is the z variable. That is why we have assumed that the wave is propagating in the z direction. So, what is the two important assumption we are taking? First, uniform distributed circuit theory, and second, wave propagation in the positive z direction. These are the basic assumption. This is the generator, resistor, L inductor, resistor, L capacitor. So, these are the basic components simply, and everything is represented by the general nomenclature which is used. This is the generator and this is the load. Now, here we are going to apply the Kirchhoff's voltage law and the Kirchhoff's current law. So, because this is applicable for the circuit theory, so this is also one sort of a circuit, that is why we are applying that. So, when we apply the Kirchhoff voltage law in any mesh or any the closed circuit, so what will be the, actually we know that voltage dropped in any closed circuit will be 0. So, actually we are taking this assumption. If we are taking this closed circuit here, that means voltage drop should be equal to 0. So, summation of the voltage drop around the central loop VZT, you are able to see this figure, this is the VZT, okay. This RIZT, R del Z, because we have taken a small component, so that by del Z will be always included, IZT. Now, the inductor, this one L del Z, del I, ZT, del T, and now after that there is this one. So, and its voltage is V Z plus del Z T. So, V Z T del V Z T del Z del Z. So, these are the equation which we are getting by applying the KVL at the central loop of the circuit. By now, what is the second step here? Now, we are going to rearrange this equation and dividing by it by del Z. Del Z divided by del Z and omitting the argument Z T. So, what we are going to do here? The first thing which is here, this will get cancelled, and then what will happen? What we have now? This one. You will have to omit the ZT, and del Z should be divided by del Z. So, this will be IR only plus L, del Z should be divided, and this will be then del I by del T, because this will be omitted and this will be divided by del Z. So, we are able to have this, then now this will be the same thing is applicable here also. This will be omitted and this will be divided by del Z. So, we get cancelled. So, what we will be able to get? Del V by del Z. And now, in the next step, this portion is taken in the left hand side. So, with the minus sign here. So, have you got how we are able to get this? So, we first thing which we are done. So, again I am helping you. The first thing, apply the Kirchhoff's law in the central loop, the equation which we are getting, same value, delete it, okay. Then divide the complete equation by del Z, cancel, del Z cancel, del Z cancel. Then omit the argument Z del Z, isko omit. That means you have to cancel it out. So, this expression 0 should be equal to R I plus L del I by del T plus del V by del Z. And the next step is taking this equation on the left hand side. Are you able to get the equation? Okay. Now, we are going to apply the Kirchhoff's current law. So, when we apply the Kirchhoff's current law at the point B, so what type of current are coming here? IZT, IG is emitting, IC and this. So, this current is coming and this current is going out. So, you are able to see on this basis V Z plus del Z IZT, this one, now this one across this, because this is the voltage and this is, we can have the inverse of R, this is the conductance. So, this equation similarly across the capacitor, this is C, we have this equation, and after this one we have this. So, I think that all of you are able to know that how this particular equation has come. Now, a replacement of this, we can have this expansion of, basically we can say expansion of this, we can have this. Similarly, C del Z and expansion of this expression, we have that, this, and expansion of Z plus del Z IZT. So, where we have expanded the Z plus del Z. And after that, the same thing which we have done for the in the case of a KVL, we have applied here, that dividing it by del Z and omitting del ZT. So, in this all expression, what we are going to do? We have divided by del Z in every expression we will divide it, and after that we will omit. Try to do it by saying yourself, same as which we have done in this expression. For getting this expression, you are able to get the current equation, which comprises of minus del I by del z GV plus C del V upon del T. Thus, the process is similar as this equation. Now, then by differentiating equation 1, which is our equation 1, this is our equation 1. So, by differentiating equation 1 with respect to z and equation 2 with respect to t, which is this is our equation 2. So, and then combining we will have the result here. So, what we will be able to do? Just I am going to have the small step for you. So, when you will differentiate it, what will you get? And for the rest, with what respect we are going to differentiate it? With respect to z. Minus del square V by del z square is equal to R del I by del z plus L del I by del t del z. This is our differentiation. And when we differentiate this equation, what we are getting? With respect to t, minus del I by del z del t plus, not plus, equal to G del V upon del t plus C del V upon del t square. So, first of all, what we will do? We will take this expression here. So, what will be the expression? Minus del square V by del t square, del z square should be equal to R del V upon del z plus L del V upon del t del z, del V upon del t del z. So, what we are going to do now? We have del V upon this expression. So, we have the value from here and we can take the value from here, and when combine this three equation, we will have this equation. So, for getting this particular equation, you have to combine this equation, you have to combine this equation and this equation. On combining this three equation, we will have able to get this particular equation. And if we similarly want to, this is the equation in the terms of voltage, but when we want the equation in the terms of current, what we have to do? We have to just reverse. We have to differentiate this current equation in the terms of z, that is equation 2 with respect to z, and the voltage equation, which is our equation 1, with respect to t, and again differentiating with respect, and then combining the equation which we get, we are able to get this equation in the terms of current. So, what we have to do is basically, first of all, we have to find out the equation in the terms of voltage, current, differentiating it with respect to z. If we equation 1, that is voltage equation, with respect to z, if we want the expression in the terms of voltage, and current in the terms of time, if we work, and then after combining we will able to get. So, this are basically the all this are basically the transmission line equations. So, this is the transmission line equation in the terms of voltage, and this is the transmission line equation in the terms of current. Now, we are able to have that also, कि voltage and current on the line are the function of both position z and the time t. The instantaneous line voltage and the current can be expressed by this equation. This is the positive direction, this is the negative one, plus I plus and V plus basically denote the in the positive direction, and V minus and I minus basically denote the in the negative one. So, now what we are going to have, we are now available with the fourth type of equation. So, first equation, second equation, third equation and the fourth equation. So, now you can replace this del t, del by del t by z omega in all the four equations, and after that divide each equation by E j omega t. The transmission line equation, the phasor form can be obtained. So, I am going to solve one for you and the rest will be as a work for you. The first equation, minus del v upon del z should be equal to r I plus L d I by dt. So, minus del v upon del z is equal to r I plus L d I by dt. So, what will be asked for you to change the del by del t, replace the del by del t with j omega. For the complete one, minus del v upon del z should be equal to r I plus L. In the place of del by I should be written as it is, and in the place of del by del t I am going to write j omega. So, r plus j omega I. For the complete, I write it with the capital I for the getting the. So, dv by dz should be equal to r plus j omega I. I am erasing the negative sign from the LHS side, so it can be handed over to the right hand side. So, what we are getting now, dv by dz should be equal to minus r by j omega I, and this term is replaced with z. Okay? So, that is why z is equal to r plus z omega L. So, similarly with the help of equation 2 you are able to get this equation, with the equation 3rd you are able to get this equation, and with the equation 4 you are able to get this equation. Okay? And of course, the gamma, which is our propagation constant, is equal to alpha plus j beta, where alpha is the attenuation constant and beta is the phase shift, and it is equal to under root of j, capital J and y, capital J r plus j omega L and y g plus j omega c. So, take it as an assignment, and similar as I have solved the equation 1, you should derive this 3. And these are the condition with the equation which I have here is for the lossy medium, but if the medium which is here with us is the lossless one, in that case what we have to do? We have to replace r equal to g equal to 0, and in that case what will be the change in the equation we have is this one, because first again the first thing I will do for you. So, what we have dv upon dz minus r plus j omega L I. So, for the lossless medium r should be equal to 0. So, r equal to 0, we are getting this equation. And similarly, you can solve for the rest of the 3 equation, replacing r equal to 0 and g equal to 0. So, here comes the end of the transmission line equations. We will continue with the next topic in the next lecture. Thank you.